Hey everyone, welcome back. This week we are going to dive into a related topic to what we covered last week and talk about confirmatory factor analysis. So I want to take a moment just before we really get started to outline how exploratory factor analysis, which we learned last week, EFA, and CFA are often related. And these are typically two of the more important analytic steps in the process of developing a scale. If you're interested in developing typically a survey measure of a construct that you're interested in. And so this is sort of a flow chart of how all that works over time. So typically you would start with instrument design in some form of a pilot phase. You might consult with experts in the area, in your area, and talk about different types of items and pilot test different kinds of items. Then you would proceed into the validation stage, which primarily was what we learned about last week, where you would collect data from a sample and run an exploratory factor analysis to see how the data you collected match your sort of hypothesis about how things should sift out. But this is very much an exploratory nature. And then the third step in scale development is instrument confirmation, which is typically using some form of a confirmatory factor analysis. And so that is where you get more specific about how everything fits together, and you may often collect data even from an additional sample. Now, you don't do this all at once. This is typically over the course of several different studies or papers, using different samples, or could even be by different research teams. You may not do all this, but that's sort of the process that goes on as we think about scale development. So we're going to focus this week primarily on confirmatory factor analysis. Well, in order to get to CFA, we really need to talk about some of the limitations of EFA. And they're right there in the name. Like the name suggests, EFA is really an exploratory procedure. It is an initial investigation into the possible structure and properties of a scale that you're interested in. It typically is not sufficient to sort of prove or show with beyond a reasonable doubt that you have a scale or a construct that will hold up consistently over time. And why is that? Typically because EFA has some limitations. First of all, you may notice that when we did the EFA procedure last week, there are no p-values. There really are there's no way to compare statistically different solutions or different rotations. Remember, we talked about oblique and orthogonal rotations, and even within there are many different kinds of each type of rotation, and there really is no way to compare those. In fact, some statistical work has been done in the last several decades to show that really, depending on what rotation you use, you can end up with an infinite number of solutions, and that makes it really hard when you have an infinite number of solutions to argue that the solution you found with those specific weights and those structures are really optimal. So that's not great. We also run into this problem of perfect prediction, and that's when, if you think about how EFA works, each item doesn't really have its own error term. What we end up doing is sort of pushing all of the error, the unexplained variation, from the EFA into one term, one single error term. And that can be difficult because we know when we look at our items in an exploratory factor analysis that the uniqueness, or the opposite, the commonality associated with each item can be very different, right? Some items are really contributing very strongly to our factors. Some items are not contributing very much at all. But we are just sort of assuming that all washes out in the end and all that gets pushed into a single term. And of course, that can introduce problems as well. So a solution is confirmatory factor analysis. So let's focus, I want to sort of help you think conceptually, moving from EFA to CFA. And let's start by going back to this SPSS anxiety scale from Andy Field. And let's focus for a minute just on the first factor from Andy Field's anxiety scale. This is what we talked about last week in the video last week. And I think I ended up calling this the computer factor or something like that. They all have, all these questions, 6, 7, 12, 13, etc., all have to do with feeling anxiety around computers or SPSS. So that's the scale that we're gonna focus on. When we run an exploratory factor analysis and we interpret our factors, we get a result something like this. And I think this was perhaps with the oblique rotation is what I used. And what's really nice is, we have this little option here that says blanks. And this is for items that have particularly low loadings, less than 0.3. And we end up with this very nice solution where we have these 1, 2, 3, 4, 5, 6, 7, 8 items that all relate to computers that all have a weighting or a factor loading of more than 0.3 on this common factor. And that's really good, right? We look at that, we think, okay, that's really great, that's really clean. Well, in actuality, even after rotation, it's not quite that clean. In fact, this is what the factor loadings really look like. Notice we specified before blanks, right? And we said, okay, I want to get rid of these loadings that are less than 0.33. So some of these questions, for example, down here, all these loadings are below 0.33. And up here, all these loadings are again below 0.33. Those may not contribute significantly to the factor, but they're still included in there. In other words, these items are still allowed to load in sort of minute, small ways onto this factor, even if we don't want them to, right? Because we would think that these are the computer questions, these are the things we want to load. But actually, when you run an EFA, you sort of allow everything to load onto everything, even in a small way. And this problem is confirmed a little bit further when it comes to actually using this factor. So if I actually wanted to use this computer factor, I would do something like predict, which is a command that we learned about this past week, where we take a factor that we found in EFA and turn it into an observed score, a factor score, that I can then use in ANOVA or regression. The tricky part is, and you can see here too, after we run this predict command, we actually can see the weights that are applied to this factor. So this is sort of like a composite of weightings of all these items. And what you see is, again, the weightings are not just on the items we want. All the other items are also contributing to this latent factor. And so really, something that seems pretty clean and is fine for exploratory work really isn't as clean as it should be. But one way around this is to use confirmatory factor analysis. Okay, so here is confirmatory factor analysis, and this is a very common path diagram, not the computer part, but the setup, for what a CFA looks like. A CFA is a much more sort of formal way to proceed with a factor analysis, where you have a very specific theory in mind, and you are testing it using a very specific model. So to add some context here, the ovals in this diagram here represent latent variables. So computer here is a latent variable. Notice here also these circles are special kinds of latent variables. We'll get to those in a moment. The path arrows here, notice this arrow going from computer to question 6, question 7, 10, 12, etc. Those are factor loadings. And the circles themselves are error terms. And these actually are also latent variables, believe it or not. And they're latent variables even in regular regression. It's something that we assume to be sort of a latent variable. So already you can see the advantage. As opposed to in EFA, when you have sort of loadings all over the place and small loadings that don't sort of count but are still there, in CFA you have specified one latent variable, and you have very directly defined all of its components. And in addition to that, Each item now, the variation in that item can go one of two places. It can either contribute to the latent factor, in which case it's a loading, or it can go in its own item-specific error term. So in EFA, we had one error term that sort of swept up everything. This is providing an error term or an error variance for each one of our items, which is a much more precise way of conducting a factor analysis. The other cool thing about this is that this is actually a statistical model. We can actually fit this model in Stata and lots of other software, and we can get fit statistics that tell us how well this model actually matches our data's underlying relationships. And so we've gone from sort of an exploratory approach to a very sort of confirmatory model-specific approach. Just a reminder here, just to hit this again, the squares here are the items. So questions 6, 7, 10, 12, 13, 14, 15. And what this is doing conceptually, this is basically like running 8 little regressions, 8 simple linear regressions. And in each one of these regressions, our latent variable is the predictor, and the observed item is the outcome. And so we're seeing to what extent do changes in this latent variable predict changes in the item. And we're going to get a loading or a standardized factor on there. And everything that's not explained by that little regression is going to go here to the error term. Okay? All right, so that's sort of a basic overview of what the CFA framework is, what it looks like. A really important component of CFA is understanding model fit. And that is the ability of a model that you have created to reproduce your underlying data. And when we talk about this, we usually talk about it in terms of a variance-covariance matrix or a covariance matrix. What this means, sort of conceptually, is that when we specify a model, we are essentially predicting a set of relationships about our variables. But we also know what the actual relationships about those variables are, which is over here. So we have a predicted model and we have an actual relationship. And what we do when we assess model fit is we sort of compare how close are these two things. Ideally, our predicted model is going to come very, very close to our observed data. And if that's the case, then we can typically say that our model is a good approximation for our data. So what's going on in CFA under the hood is that we're actually comparing these covariance matrices, the observed and the predicted, and we're seeing how different or discrepant they are. If they're basically the same, that's really good. And it means that our model fits the data well. And this is a hypothesis that we typically test using a form of a chi-square test. So at this point, I'm going to introduce a series of different fit statistics. I don't want you to get overwhelmed here. I know that I'm throwing a lot at you in this week. The cheat sheet, which I'm going to pop to just for a second, is on Blackboard, and it provides a nice quick summary of all of the fit statistics that we're going to talk about and what we're looking for with each one of those. So that's a great resource. I'm going to talk briefly about each one of these fit statistics. I'm going to show you the notation and then also their purpose. Basically, there are different kinds of fit that are measured by each fit statistic, and each fit statistic has its own sort of rule that goes with it. I am not expecting you to memorize these at all. I've only become comfortable with these because I work with them all the time. People look these up all the time. It is completely fine. What I would like you to take away from this is, one, that there are lots of different ways of determining model fit. 2, the extent to which these things agree with each other further validates the strength of your model. And 3, each one of these statistics is measuring fit in a little bit different way. Okay? Alrighty. Now, we're going to talk about chi-square. Chi-square is sort of the original fit statistic. This is the first and in some ways the strongest fit statistic that we have. Basically, what the chi-square represents, as my cat joins me. Okay, and we're back. So the model chi-square is kind of the overall measure of fit. It's the first thing we look for. It's represented by the Greek chi-square sign, and the degrees of freedom for the chi-square test are equal to the number of data points you have minus the number of estimated parameters. And we'll get into very specifically how you calculate those things in just a little bit. So this is an overall test. It tests the null hypothesis that your model fits the data well. In other words, that the covariance matrix for your model is very similar. Your model covariance matrix is very similar to your observed covariance matrix. And so what's interesting about chi-square, typically when you think about chi-square, you think about significance. You want to find significance. Actually, with chi-square, you want to find non-significance, because what that means is there isn't a significant difference between your observed data and your predicted data or your model data. And so in other words, it means that your null hypothesis of this test is that the data fit well, and that's what you want to see. You don't want to reject that null hypothesis, although it's often does happen. The issue is there are a number of very common problems with chi-square. A bunch of simulation studies show that it's way too sensitive to sample size. It rejects acceptable models a lot more often. So what this means is in a really, really large data set, the chi-square may be significant when actually the data and the model actually fit pretty well. And so one way to think about this is it has a very high type 2 error rate, which means it has an issue with power that gets worse as sample size increases. And so often we can't just look at chi-square. We need alternative methods. Although if you have a non-significant chi-square, that's a really good thing, because that typically means that your data fit the underlying model pretty well. There are a number of other incremental fit indices. And a lot of these incremental fit indices are comparing in some way your model to the fit of a baseline model where all the paths are fixed to 0. And so one way to think about this is a baseline model for our computer example would be that none of the items load significantly onto this latent factor if there's no relationship between any of the observed variables and the latent variables. Of course, this is sort of an easy model, right? It's the simplest model as a baseline, but of course, in almost every case we're going to reject this. But the goal is by how much. You were seeing how much better, what increment is your model better than this baseline model. So the incremental fit indices, one is called CFI, or the Confirmatory Fit Index. The formula is here. And essentially each one of those D's is equal to the chi-square value minus degrees of freedom, where degrees of freedom are the degrees of freedom for your model. And if CFI ever gets to be larger than 1, it's sort of set back at 1. If it's less than 0, it's set back to 0. So basically you see we're subtracting this quantity here for the null model minus the proposed model and dividing by the null model. The values for this typically range from 0, which means terrible fit, to 1, which is perfect fit. But ideally, we're looking for very high values, which are above 0.95. And these formulas and things come from David Kenny, who's at UConn, has a really great website on different model fit statistics. So I want to shout him out there. Then we have another incremental fit index called the Tucker-Lewis index, or TLI. This one is a little bit different than CFI because we get an additional penalty for model complexity. So we're actually dividing instead of subtracting by degrees of freedom. So more complex models, that value gets smaller a lot faster. but the setup is very much similar. We have some null model minus some proposed model dividing by the null model minus 1 in this case. Again, the values range from 0 to 1, 0 no fit, 1 perfect fit. TLI is generally a little more conservative. It'll almost always reject models more often than CFI. But again, the threshold typically is you're looking for 0.95 and above. I think on the cheat sheet I say 0.9 is acceptable, and that's generally the case, although we want this thing as close to 0.95 as possible. So those are our incremental fit indices. Then we have what are called parsimonious indices. So these are models that are really testing the complexity. These are fit statistics that are testing the complexity of your model and seeing the extent to which that matches your underlying data. There isn't this idea of comparison to a null model. It actually is sort of comparing to a model that's 1 degree less complex. And so the formula, or the key threshold we're looking for RMSEA, or root mean square error of approximation, ideally is below 0.06. So we want lower values for RMSEA. We want higher values for CFI and TLI. We want lower values for RMSEA. Then we have absolute indices. I think the only one we have here is the SRMR, or standardized root mean square residual. This has a crazy formula. So basically what this is measuring, it's designed to standardize the difference between the observed correlation matrix and the predicted correlation matrix. So you want the difference to be as small as possible. So 0 would be great. That's perfect fit. And there's no penalty for model complexity. Typically the cutoff for SRMR is, again, 0.05 or so, or maybe even 0.1. I can't remember what I said on the cheat sheet. Here we go, suggested cutoffs. So for chi-square, ideally, again, just to recap, this is all on the handout. We're looking for a non-significant chi-square, but that's typically pretty rare, especially in large samples. For CFI and TLI, we're looking for values greater than 0.95. For RMSEA, we want things smaller than 0.06. We can also calculate a confidence interval for this, and there we don't want that to contain 0.08. And SRMR, 0.08, that was the threshold, is what we're looking for. See, we often don't have these things memorized. We have to look them up. If you're looking for good papers to cite on this, Hugh and Bentler is the standard for those cutoff criteria. Rex Klein also mentions this quite a bit in his really good textbook on structural equation modeling, of which CFA is one small part that came out a few years ago. Okay, so now we're going to talk about building a CFA model and a few things you want to keep in mind. So every path, every correlation, every variance is what we call a parameter. It's something that the model is going to estimate. And the big rule for estimating a CFA model and all other structural equation models is that the number of parameters in a model cannot exceed the number of data points. One way to think about this is inputs and outputs. Data points are your inputs. You have to have at least as many inputs as you have outputs. And if you don't, this model will not run. It will be what's called under-identified. If you have more parameters that you want to estimate than data points, it cannot be estimated using SEM. Data points are pretty straightforward. They're calculated using this formula where P is the number of observed variables. So in our example, we had 8 observed variables. So we have 8 times 9 is 72. Divided by 2 would be 36 possible data points in our CFA example with 8 items. If you had 3 observed variables in your CFA, it would be 3 times 4, which is 12, divided by 2 equals 6. So those are your data points. Okay, so a key step in this is determining, does the model that I've specified have enough data points to actually be identified? Am I going to get a solution? So here's an example here. I've got this latent variable of what I'm calling negative affect, And I have 3 observed variables. I have someone respond about how angry they are, what level of shame, and what level of sadness. So based on those 3 items, I'm going to try to construct a latent variable for negative affect. Okay, so in this case, we have 3 observed variables, which means 3 times 4, which is 12, divided by 2, which equals 6 possible data points. And that means we can have no more than 6 parameters. Ideally, we actually have less than 6, because then we get model fit statistics. If we have 6, it's what's called a saturated model, which means we don't get those fit statistics. So in this case, we need to count up our parameters. And the rules are every square and circle gets a variance. So 1, 2, 3 variances, 4 variances here for this latent variable, and then 3 paths, 5, 6, 7. So in this case, we have 7 parameters and only 6 possible data points. This model is under-identified. It can't be estimated. Another issue with this is that this latent variable that we have here doesn't have a metric. In other words, we haven't assigned or set a scale for this latent variable, and so it's unclear what it means to have a score, for example, of 1 on that latent variable. So there are a couple solutions to this that are pretty standard in SEM software. One approach is to constrain the variance of the latent variable to be equal to 1. So that effectively makes the latent variable something like a z-score with a mean of 0 and a standard deviation of 1. This frees up 1 parameter. So now I'm only estimating 1, 2, 3, 4, 5, 6 things, 6 parameters, and I have again 6 data points. So this model would actually be able to be estimated. Another approach that's very common is that you fix one of the factor loadings. So in this case, we can fix the factor loading on anger to be 1, and that sets the scale. So now the scale of the latent variable is the same as the scale of this item, and it frees up again 1 more parameter. So now we're only estimating 1, 2, 3, 4, 5, 6 things, and we only have 6 data points. So this will be able to be estimated. Either way works, and it won't affect the fit indices. By default, Stata uses this approach. It constrains the very first item to be at 1. Okay, so we're going to talk just a little bit about modification indices. Now, as you see here, we actually took a step in the previous slide here. We constrained this path to be equal to 1 in order for this model to be identified. So what we actually did was we made a model modification. And the larger case of those are called modification indices. These are setting specific constraints in an effort to improve model fit. Stata will provide you with these. So basically, Stata will take a model that you've run and will provide suggestions for how to improve the fit of your model. However, I think of this, and a lot of people think of this as Pandora's box, because the whole point of CFA is when you take a model like this, negative affect in these 3 items, you're specifying a very specific set of relationships between these variables. And the more complicated you make it, and the more you make decisions based on your data and not on theory, that can create a lot of problems down the road. And so in general, we don't recommend you making modifications, but occasionally it can be helpful, particularly in an exploratory type way, seeing how the model is functioning. So here are some examples of what this looks like. If you run this command after you run a CFA, estat m indices, you get model modification indices. And basically what you do is you're looking for the modifications that would produce the largest change in chi-square or model improvement, and that's this column right here. So in this case, if we look right here, the modification with the largest improvement is this specification right here. So what this says is add a covariance between question 6, the error term of question 6 and the error term of question 12. And that would improve our model fit by 108 chi-square points. However, you should really proceed with caution, because does that make sense? Is there a reason, sort of theoretically, why the error terms of question 6 and question 12 should be related to one another? There we go. So a common time when you might do this is when you are measuring the same item across time longitudinally. So let's say we gave our Andy Field Statistics Anxiety Questionnaire at the beginning of the semester, the middle of the semester, and the end of the semester, and we want to measure change over time in anxiety. Well, the first thing you have to do is estimate anxiety at each of those times. And of course, you're using the same questions. And so it's common in that approach to actually covary the responses on each question. It's the same question over time for each person. So that's one case of when you might make a modification. But again, you really want to proceed with caution and make sure it makes sense to make those modifications. Okay, we're on the home stretch. You've done a great job. I'm sure you're with me the whole way. If not, that's okay. Well, this stuff takes time. So just one more word in sort of how to present these estimates. So again, we talked about this at the beginning of the lecture. This is a path diagram. And this path diagram shows our formal relationship between our latent variable and our observed variables. And we have our factor loadings here, and we have our specific error terms here. This is typically how we might present the results of a confirmatory factor analysis. These are what are called the unstandardized estimates. And in this case, the loading all the way to the left here has been constrained to 1. And interestingly, question 7 also has a value of 1, and question 18. So all three of these questions actually have very similar loadings. And then here are the loadings for the other items specified along the side here. The variance of our latent variable computer is right here. It's 0.55. Since we constrained this, we now get a variance for our latent variable. It has a mean of 0 and a variance of 0.55. And then here are the size of the error variances. So the larger these error variances are, the less a particular variable is contributing to the overall solution. So the sort of strongest contributors are the ones with the lowest error variances. So for example, question 13. And then these are the intercepts. So these are the intercept values, just like in a little mini regression. We have a regression coefficient, we have an error term, and we have an intercept. And then this is typically how we might portray model fit. It's also common, and in Stata we can get what are called standardized estimates. And in standardized estimates, we fix that variance up here to 1, and then we now get a estimate for each of our items, and these are typically interpreted in standard deviation type units. So you'll see here you can sort of compare across the units, and this is actually a nice case where almost all of our loadings are very strong and all pretty close to one another. So that shows pretty uniform fit, and of course here are our fit statistics in this case. Okay, so the practice video is going to walk through a little bit more of how to conduct confirmatory factor analysis in Stata. For more reading and examples, I recommend Chapter 1 of Alan Aycock's book, not the one for class, but another book he wrote called Discovering Structural Equation Modeling Using Stata. It's a very good book. That first chapter is available for you on Blackboard. Tim Brown has written a really excellent book all about confirmatory factor analysis for applied research. The whole thing is great, but the introductory chapters provide a nice overview. And then Chapter 9 of Rex Klein's book, Principles and Practice of Structural Equation Modeling, is another great place to look. So this is just sort of cracking the surface of what's out there in terms of confirmatory factor analysis. But again, just to recap, Compared to EFA, in EFA, we're just sort of exploring. We're throwing our items in and sort of seeing how they sift out. We're assigning loadings. We're looking for how sort of the pattern of loadings matches up. But we're also allowing a lot of smaller loadings under the surface that may not actually align with our theory. In confirmatory factor analysis, we're getting much more serious about things, and we're actually specifying a latent variable and a set of items, and we're being very specific about the relationship between the latent variable and the items, and each item has an error term. And then using SEM, or structural equation modeling, we're actually able to get models of fit that tell us how well our underlying data match the model that we had in mind, so we can kind of see whether or not we've got anything specifically. So thanks for your patience. I know this was a long one. Hopefully that was helpful, and the demonstration should hopefully clear up some more questions too. Thanks and good luck.